Hello, and welcome to this presentation on bistatic mmWave mapping in obstructed environments using double-bound signals. My name is Henk Wymeersch, and today I will be discussing our approach to utilizing double-bound signals for mapping in complex environments. This work is a collaboration between Tampere University and Chalmers University of Technology. In recent years, there's been a great interest in utilizing mmWave communication signals in 5G and 6G, particularly from the perspective of localization, sensing, mapping, and SLAM, which stands for simultaneous localization and mapping. In traditional radio SLAM systems, the user combines information from both line-of-sight and non-line-of-sight paths to determine its own position and map objects in the environment. Typically, non-line-of-sight paths are assumed to be single-bounce paths, and multi-bounce paths are often discarded. However, recent research shows that these higher-order reflections can actually be utilized to enhance system performance. Our approach is based on the principle that both line-of-sight and single-bounce non-line-of-sight paths can be identified using geometric consistency, which allows us to simultaneously localize a user and map part of the environment. Any remaining paths are generally considered clutter or higher-order non-line-of-sight reflections. Our key insight is that double bounce paths, which involve two interaction points with the environment, as shown in the figure, can actually provide valuable information. By recognizing one interaction point in a double bounce path among the single bounce path interaction points, we can estimate the second interaction point, allowing us to discover new landmarks that were previously overlooked. We validated our approach with experimental data. In one experiment, we measured 45 different user equipment locations, detecting a total of 410 propagation paths. The data collected through this experiment helped us to analyze the potential of using multi-bounce paths for mapping and localization. The experiment was conducted at a frequency of 60 GHz with a bandwidth of 400 MHz. The signal type used was a PRS, or positioning reference signal, with a comb factor of 2 and a subcarrier spacing of 120 kHz. We employed 16x4 antenna arrays at both transmitter and receiver with a beam width of approximately 10 degrees. Here we illustrate the difference between single bounce and double bounce paths on the map. The base station is shown with a blue triangle, the user trajectory in a blue curve, and the estimated user locations with black crosses. On the left side, the single bounce landmarks are shown in red. On the right side, by processing the remaining paths, double bounce landmarks could be detected and localized, shown in pink. We see that several new landmarks were discovered, which were invisible among the single bounce paths. In conclusion, we've demonstrated that multi-bounce paths, traditionally considered as a nuisance, can actually be a valuable asset for mapping and localization. By incorporating these additional interaction points, we can discover new landmarks and potentially also improve user localization performance. For more details, see the link below.